right, let's talk about two important things that I want you guys to know. Okay, one of them is that the electron that we just talked about, moving from one energy level to the next, is a wave and a particle. Okay, so light is a wave and a particle, and electrons are a wave and a particle. So we call that wave-particle duality. Okay, it has properties of a wave and properties of a particle. Okay, this is the whole thing with the quantum mechanics. Okay, this is the whole thing with a lot of physicists. So if you really look at it, a lot of physicists, theoretical physicists, and physics people in general, physics PhDs, contributed a lot towards this chapter, like Albert Einstein and Schrodinger, Maxwell. Okay, all of these famous physics scientists did a lot with quantum chemistry. So an electron is a wave and particle. It has and displays behaviors of both. Light is both a wave and a particle. It displays behaviors of both. Okay, so you know what a particle is. So a particle may be just something like that. Okay, but what is a wave? Okay, what is a wave? So we're going to call a wave an oscillating piece of energy. So within that wave carries energy. You know, the radio waves, they carry energy. It's just energy that you can hear. Okay? That white light carries energy. It's just energy that you can see. Okay? The microwave radiation is energy, but it's energy that could, warm your food. Okay? The UV radiation from the sun is energy. It's just energy that could make you tan or, mess up your DNA, stuff like that. Okay, but all of these are waves. They oscillate. Okay, they go back and forth, back and forth. That's what we mean by oscillating. Okay, back and forth. So let's look at some features of a wave. Okay, so what are the parts of a wave? So a wave looks like this. Okay, so back and forth, back and forth, back and forth we go. Okay, the topmost part here is called the amplitude. This is where the wave gets its energy. The amplitude of the wave, that's the peak. Going from one peak to the next peak, okay, or going from one minima to the next minima. Or going from any point to the next corresponding point in the repeat of the oscillation. Okay, that's called wavelength. Okay, wavelength, and it has the symbol lambda. Lambda. That just means wavelength. Okay, it's a length. Okay, typically in this chapter, and when we talk about waves and wavelengths, the units are going to be in nanometers. They can be in meters. Okay, they can, but these are so small entities that they'll be in nanometers. Okay, so 1 nanometer is 1 times 10 to the minus 9 meters. So top to top, maxima to maxima, minima to minima, that's the wavelength. Okay, it has the symbol lambda. So it's oscillating and it's also traveling. So if you can imagine there's a person here Okay, there's person 1. Okay, and here's person 2. Person 1 and person 2. So this wave is oscillating. Okay, I'm going to pick a point on this wave. Okay, let's just pick this one here. Okay. Okay, I'm going to pick 2 points on this wave here. And the question I have to ask you guys is, how many times will this unit on this wave pass through this person versus how many times this point on this wave passes this person? Okay, which wave, is it wave 1 or wave 2? Which point will get through this person faster and more often? Because remember, it's back and forth. Okay, which one will reach this person or see this person faster and more often because the wave repeats? Wave 1 or wave 2? Okay, everyone agrees it's wave 2, so we say wave 2 has the higher frequency. Okay, it's sort of like the speed of a wave. Okay, frequency. How fast does a point pass through something or someone? Okay. So frequency. Okay, it has the units cursive V. Okay, cursive V. And it's how fast the wave travels, the speed of the wave. Okay. And the units of this are going to be in 1/seconds. How many times per second? Per second. Okay. How many times per second the wave passes a particular point. And 1/second is also called hertz. Frequency, or 1/second, is called hertz. So what is 1/second called? Hertz. Okay, what are the units of hertz? 1/second. Okay. So how many times per second this point passes some point? Passes some arbitrary point. Okay. So Gerardo, you said wave 2 has what, higher or lower frequency than wave 1? Yes, that's correct. So wave 2 has the higher frequency. Okay, but what do you notice about the wavelength? Very good. Okay, it's shorter. Okay, so this is one relationship that I'd like for you guys to know. Okay. That is, as your lambda goes up, what happens to your frequency? Goes down. Okay, as your frequency goes up, what happens to lambda? Goes down. Okay, so lambda, wavelength, and frequency are indirectly or directly proportional? Indirect. As one goes up, the other goes down. Indirect. Okay, indirect. They are indirectly proportional. So wavelength and frequency are indirectly proportional. One goes up, the other goes down. Okay? So that's one relationship between wavelength and frequency of a wave. So we see these things here. These are also waves. Okay, the light that's coming and hitting this. Okay, the light that's coming in and hitting this, going through this lens. Okay, that's a wave. The light that's coming through and hitting this, okay, those are also particles. Okay, that's why quantum mechanics is so difficult for many students. First of all, it's its own branch of math. It's different language than Newton's calculus. Okay, because you're talking about or trying to describe something that's both a wave and a particle. Okay, so look at it here. Okay, so it's a wave and a particle. That's called wave-particle duality. Right, if we take the wavelength and multiply it by the frequency, we get speed. Speed. Okay, And this speed I'm going to call, for the electromagnetic spectrum, the speed of light. So C here is called the speed of light, and that's a constant. So let's write this equation again here. So you guys mentioned that they are indirectly proportional. As one goes up, the other goes down. But if you take the product of wavelength and frequency, you get the speed of light, which is 3 times 10 to the 8 meters per second. So that's a constant. Okay, I'll give that to you on the exam. Okay, so this is talking about electromagnetic radiation. This is the same thing you saw here. Okay, any type of radiation that has this type of wave feature. So the electromagnetic spectrum is radiation, but it's two waves that are actually traveling perpendicular. Okay, one is an electric field wave, and the other is a magnetic field wave. They're traveling perpendicular to one another. So an E field wave traveling perpendicular to a B field wave. Right, an electric field wave, and it's traveling perpendicular to a B field wave. This is, the characteristics of the electromagnetic spectrum. And so that's one thing. And the other thing is that they all travel at the speed of light, 3 times 10 to the 8 meters per second. Okay, so it's traveling perpendicular to a B field wave, and that speed in which they travel is the speed of light, 3 times 10 to the 8 meters per second. Okay, so in the electromagnetic spectrum, we have an E field, okay, and then traveling perpendicular to that is a B field. Right, so what is this electromagnetic spectrum? Okay, it's an electric field wave traveling perpendicular to a B field wave. They travel at the speed of light, 3 times 10 to the 8 meters per second. But what is this spectrum? Okay, the spectrum contains a lot of everyday energy sources that we use. Okay, so it's not in color, but on Canvas I've uploaded a color version of the electromagnetic spectrum. So there was a scientist, James Maxwell. Okay, Maxwell over here. And they interviewed the Facebook CEO. I saw this interview a long time ago, so this story struck with me. And they asked him, the Facebook CEO, what scientist does he admire the most? And he said he admires Maxwell. Okay, Maxwell. Okay. So the interviewer asked him, why does he admire Maxwell the most, James Maxwell? He said because he elucidated, he constructed, or he determined the electromagnetic spectrum, without which we don't have many of the technologies that we take for granted today. So Maxwell is probably considered one of the more brilliant physicists and scientists that we have. So what is this spectrum? Okay, so it's a spectrum here that has wavelength. Okay. Here. Okay. And you can see here that we go from 10 to the minus 3 to 10 to the 13. Okay, this is the wavelength, it's lambda. Okay, so this is increasing this way. And then we have frequency in the spectrum. Okay, remember, what are the units of frequency? Hertz. Hertz. Okay, so we have 10 to the 26th, 10 to the 20 here, and then we have 10 to the 4th here. So this way it's increasing, or so the frequency is increasing this way. Okay, here we have a low wavelength, high frequency. Okay, around this region of the spectrum we have gamma rays. Okay, so is that high energy or low energy? Okay. Well, it's very high energy. Look at the next level down. Okay, we have 10 to the minus 4, 10 to the 18. I know it's hard to see. 10 to the 18 frequency. We have X-rays. Okay, X-rays are used to actually image. Okay, they're used as imaging. So do you think that's high energy or low energy? Okay. Can't have too many X-rays, they can penetrate your flesh, right? So this region of the spectrum is more high energy. Okay, look at the next level of energy, the radiation, ultraviolet. Okay, you may have heard about the dangers of UV radiation. Okay, so these are high energies. As you move further and further towards higher wavelength, lower frequency, you get less and less low energy radiation. So here we have high wavelength, low frequency. Here we have low wavelength and high frequency. So that's the spectrum. So within this region of the spectrum, there's a tiny slit. There's a tiny, tiny, tiny portion. Okay, that's visible. There's a tiny region that we can see. Okay, tiny region that we can see. Okay, this is the visible region of the electromagnetic spectrum. All right, and you take that tiny slither and you can split it apart into the components of white light, which we saw here. Okay, it's going to be Roy G. Biv. All right. So I uploaded a color version of this spectrum on Canvas, so you can take a look at it. But you know, everything that we use and utilize in life, okay, some way or some form revolves around this type of radiation. Okay, we listen to the radio, okay? That's radiation from the electromagnetic spectrum. Okay, we heat our food. Okay, that's radiation from the electromagnetic spectrum. We see colors that our eyes and visual cortex can see. That's radiation from the electromagnetic spectrum. Okay, we go out in the sun and we get UV radiation. Okay, that is energy from the electromagnetic spectrum. You go to the hospital and get X-rays. Okay, how many of you have gotten X-rays before? Any athlete? Okay, don't they cover you up with lead, a lead vest? Okay, because the lead will absorb all the X-rays, so it doesn't spread all throughout your body. Okay, when you go to the dentist, you get an X-ray. Okay, so that is energy from the electromagnetic spectrum. Okay. Gamma rays, I don't know, gamma rays, isn't that what made Hulk the Hulk? Okay, okay, that's very, I don't know if, maybe you know better than I do if gamma rays are found here, but I think they're found in the planets or the solar system. But anyways, gamma rays are high energy, okay, high frequency, low wavelength. So everything that can be destructive to us, okay, especially a high dosage of X-rays, and anything that we just see and hear, all of that is radiation. All of that is energy from the electromagnetic spectrum. Furthermore, all of these radiations from the electromagnetic spectrum are really just the E field wave traveling perpendicularly to the B field wave. Okay, what is the electromagnetic spectrum? What are the two waves? Okay, the E field perpendicular to what? B field. Okay, what is the E field wave? Okay, electric field. And what is the B field wave called? Okay, they're traveling perpendicularly. Okay, you can call it the electromagnetic spectrum, electromagnetic radiation, electromagnetic waves. And what speed do these guys travel at? 3 times 10 to the 8 meters per second, speed of light. Very good. Okay. All right, so all of these travel at the speed of light. All of these travel at the speed of light, 3 times 10 to the 8 meters per second. All right, so here's an equation that I will give you on the exam. And I think there's an error in page 5 of your notes, but we'll address that. First of all, one is the speed of light is equal to wavelength times, wavelength times frequency, okay? And then energy, okay? The energy is equal to h times v. Okay, this h is called Planck's constant. E equals hv. This E is equal to energy, h is Planck's constant, and v is the frequency. Okay. So let's just write that down here on page 5 of our notes. So E is equal to the energy of that wave. Okay, the energy from that particular type of radiation, whether it's visible light, whether it's red light, whether it's blue light, whether it's X-ray, whether it's UV light. Okay, V is the frequency of that electromagnetic radiation wave. Okay, and then H is Planck's constant. Okay. And Planck's constant is, I think Planck's constant is joules times second. Yes, okay, so the units here are joules times second, okay, which is 6.63 times 10 to the minus 34. All right, so if we take E equals h times v, we know that c, speed of light, is equal to lambda times v. So this implies frequency v is equal to c over lambda. So we can plug that into here. And then the energy is also equal to hc over lambda. Okay, so this is not right. Okay. So okay, from this equation 1 and equation 2, you can get equation 3. All right. So these are the two equations, actually 3, but really all you need to know is 2. Okay, C equals lambda times V. V is frequency. E is h times v. Okay, h is Planck's constant, which is this number here, 6.63 times 10 to the minus 34. This gives us the energy of that electromagnetic radiation. All right, finally, one more thing I want to do, then we'll do this problem, and then I think I'll call it a day. Just remember here what we also mentioned so the electrons are a wave and electrons are a particle. So here I'll imagine an electron as a particle. Okay. So we'll have energy on the y-axis. I'm going to excite this electron. Let's put in another energy level here. Okay, n equals 4, n equals 5, n equals 6. Okay. I'm going to excite it. Okay, so if I hit it with a quanta, Remember that term quanta? Okay, if I hit it with a quanta, it will get excited. Okay, so we're going to call this excitation. Okay, then what happens after excitation of that electron when it gets excited from one energy level to the other? What happens? I think you mentioned it, Wusong. What happens to the electron after it gets excited? Okay, we call it relaxation. Okay. Okay, it will relax back to its original ground state. Okay, but as it relaxes back, it's going to release energy. Okay, and what type of energy will it release? Okay, it will release energy that is in the electromagnetic spectrum. Okay? It can release energy anywhere in this region of the electromagnetic spectrum. Okay, in some cases, yes, it will release energy that you can see. Okay, that you see that black periodic table. Okay, those are all emission spectra. You excite the electron, it relaxes, it emits. So sometimes we call this excitation, and as it relaxes, we call it this also emission. Okay, that emission could be visible, which you see there for each element. That emission could be UV. That emission could be radio waves. That emission could be microwave radiation. Whatever it is, that emission comes from that electron. Okay, and there's billions, maybe trillions of these that are all doing this in synchrony. So that emission comes from the electron going back down to its energy level. Okay, so excitation, relaxation, and from relaxation we get emission. What will it emit at? Okay, what energy will it emit? It will emit anywhere in the electromagnetic spectrum. Okay, the emission is anywhere in the electromagnetic spectrum. All right, let's do this problem here. All right, the energy of a photon. So a photon is a light particle. Is 5.87 times 10 to the minus 20 joules. Okay, what is the wavelength in nanometers? Okay, wavelength is nanometers. So we are talking about a photon. What do you think about when you think about a photon? You think particle. What do you think about when you think about wavelength? You think about wave. Okay. All right, so here is a photon that is a particle, but it has a wavelength that it's asking us to find. So there's that wave-particle duality again. Okay, is it a particle? Yes. Does it have wave features? Yes. Wave-particle duality. Okay, so the energy of the photon is 5.87 times 10 to the minus 20. Okay, so we'll do energy equals h times frequency v. The energy is 5.87 times 10 to the minus 20. And wavelength. Okay, so let's do the frequency first. So 5.87 times 10 to the minus 20 joules. Okay, divided by h. Equals frequency. Okay. So 5.87 times 10 to the minus 20. Okay, divided by 6.63 times 10 to the minus 34. Okay, I'm getting 8.85 times 10 to the 13. The joules cancel hertz. Okay, hertz. Okay, make sure you know that the unit is hertz. So that is the frequency. Let's go ahead and find the wavelength. So what do these travel at? What's the speed called? Speed of what? Light. Okay, so that's c, which is 3 times 10 to the 8 meters per second. So we got our lambda that we want to solve for. Lambda is equal to c over the frequency. Okay, c here is 3 times 10 to the 8 meters per second. I'll give you that constant. So, all right, this is 8.85 times 10 to the 13 hertz, but hertz is actually 1 over second. All right, the second cancels, so we are left with meters. So 3 times 10 to the 8 divided by 8.85 times 10 to the 13. Let's do that on our calculator. Okay, I'm getting 3.39 times 10, or 3.40 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the minus 6 meters. Okay, let's just go ahead and convert that to nanometers, just for by convention. All right, so to convert that to nanometers, I'll just do okay, it's 1 nanometer. Nano is small. Okay, nanometers is small. It's 1 times 10 to the minus 9 meters. Okay. About 3,398 nanometers. Okay, that is the wavelength of this photon. Okay, and that is the answer. That's the wavelength. Okay. All right. Quickly here, I'll just take 2 more minutes. The Bohr depiction of the atom. All right. I'm taking it really quickly here because I kind of went over this already. But what Bohr actually mentioned was that these electrons are in energy levels. Okay, so you excite it, and then they relax. As they relax, they emit. So excitation, emission, excitation, emission. Okay, and he had them as energy levels. Okay, what we know now is that electrons, yes, they reside in energy levels, but they also reside in orbitals. Okay, so the electrons can be excited or promoted. They have wave-particle dualities, but sort of in maturation, how they improved upon this is that electrons, this is going from 1900s to 1960s, 1970s actually, electrons reside in orbitals. Okay, these orbitals have names. Okay, one of them is called the s orbital, one of them is called the p orbital, one of them is called the d orbital, one of them is called the f orbital. Okay, but before then, in the 1900s, 1913 or so, Bohr, working on the hydrogen atom, said electrons reside in energy levels. Okay, but now we know that they reside in very specific orbitals. Okay, they have shapes. You see these? This is an orbital. Okay, an orbital. Okay, so we'll talk about this on Monday. Okay, so we'll go over just a little brief overview. We'll go over this equation, Tuesday. And then we'll talk about electron configuration.